Assalamualaikum and very good good evening to all of you. Before I start my lecture, I want to introduce myself. My name is Badrul Ariffin bin Badaluddin, and I will give a lecture about the second law of thermodynamic. Before I go further in this topic, I will intro you about the second law. Okay, the second law of thermodynamic is key to the analysis of thermodynamic cycle. In this lesson, we will discuss the limitation of the first law, why we need the second law of thermodynamic. As we know, the second law is an expression of tendency that over the time different in temperature, pressure and chemical potential. Okay, I want to give you an example. A cup of hot coffee that does not get hotter in cooler room. That is from the first law thermodynamic. The first law tells us that the decrease in the internal energy of the cup of coffee is equal to the increase of the internal energy of the surrounding air. That is, in the first stage, the temperature of object is higher than temperature surrounded. When by time pass, the temperature of object will be equal to the temperature of surround. Okay, I will continue to the new set topic that thermal energy dissolved. Thermal energy dissolved can exchange an infinite amount of heat with the system that temperature of thermal dissolved never change. So, we need to develop an understanding of second law thermodynamic in order to address issues relating to spontaneous, equilibrium, and efficiency. Before we study the second law, however, it will be most helpful if we get a better understanding of the nature of the three types of cycle. That is, there is three of type of cycle, that is heat engine cycle, refrigerator cycle, and heat pump cycle. In this lesson, we will learn how individual device or process work together to carry out the three different type of cycle. So, I continue to the heat engine cycle. Before I go to the heat engine cycle, we must know about heat, thermal, this the heat determinant are bodies that can exchange an infinite amount of heat with the system. The temperature of thermal reservoir never change. The system transfer heat to the thermal reservoir called a heat sink. Heat source is a thermal reservoir that transfer heat to the system. As an example, Earth's atmosphere, large body of water, vapor condensate of constant pressure. Three type of thermodynamic cycle, that is for we can see here for power cycle, you have a WS as a purpose produce, QH input, QC output always. For refrigerator cycle, we use WS as input, QH for waste or output, and heat pump cycle we use WS as input, QC as output and waste. For power cycle, we analyze the cycle. The traditional sign convention is that outward, onward, and heat flow are considered positive in the direction they are shown in the diagram. Therefore, QH and QC are both positive. This is the first law for the cycle, and the efficiency of our cycle is R when, as we know, one is a is complete cycle. That is we consider as one. This is diagram. As we know, you queue into the process, and we can get one net, and this QC is output always. Here is a diagram of system that undergoes a closed power cycle. The fluid flowing through the 4 units of piece of equipment is called the working fluid. As we know, pump will W in will inside the pump and flow through the boiler. There is a Q in and flow to the turbine. From the turbine, we can get W out. Flow to the condenser. Says is a Q out and flow back to the pump. Note, that is work by system is equal to work out minus work in. For the second cycle, there is a refrigeration cycle. Purpose remove QC from the cold reservoir. Input WS waste QH to the hot reservoir. First law of the refrigeration. That is QH is equal to W net plus QC. So the efficient of performance for the refrigeration cycle is this is the coefficient of performance for the refrigeration cycle. This is a diagram that we know that QC, Qin, Win, and QH is out from the cool to the hot. As we know refrigerant, we produce cool gas, cool temperature that from the in, and we release the hot temperature to the outside. It is a diagram of system that undergoes closed refrigeration system. This is compressor. Boiler. Then in, we produce to the boiler. There's a Q up, go to expansion valve. Will be go to the evaporator. There's a Q in, and will be a cycle. So the working fluid is called a refrigerant. And the last cycle, there is a heat pump cycle. Purpose that transfer QH to the hot receiver, input WS waste QC. First law of heat pump is and the coefficient is a reverse from the refrigerator cycle. There is COP of heat pump is 1/1 minus QC over QH, but COP of is 1/QC over QH minus 1. This is diagram that are for heat pump. This QC and W heat pump will be inside and QH as a waste. For the component of heat pump cycle, there is a diagram of a system that undergoes closed heat pump cycle. The working fluid is sometimes called a refrigerant. You can see here, the compressor W in and the condenser Q out and go to the expansion valve, go through the evaporation that QC is in and go to the compressor back. There's a call for a heat pump cycle. So as we know that I covered 3 of cycle, that is heat engine cycle, refrigerator cycle and heat pump cycle. So I will continue to more understanding in this cycle. Here are some example problem based on the material in this lesson. For exercise 1. This is information from the question, that is heat pump provide QH that is 775 megajoule per hour. I'm sorry, megajoule per hour. W heat pump is 4 kilowatt. Price for heat pump is 0.087 kilowatt per hour and operation time is 100 hours. That will be what is we gonna find. This is COP of heat pump. And we also can calculate the cost saving. for the owner to pay by a month. Okay, before we start, begin writing the definition of COP of heat pump. That is we can use this as a equation 1. To evaluate the COP HP. We get the value of is 28.43 kilowatt watt the unit. After that, how much it will cost to deliver QH to the home using an electrical resistant heater. An electrical resistant heater at best convert all of the electrical work supplies W into heat release into the home QH. Therefore, in order to get 28.83 kilowatt into your home, you must buy 83 kilowatt of electrical power. That is this is the word resist. That is 28.83 kilowatt. Now we can determine how much it would cost to operate the resistant heater for 200 hours a month. Cost resist that we can find, there is a 866.67 cents per month. So now we can apply to determine the cost operating the heat pump for a month. There is a equation that is price time by so we can have a cost for a month, heat pump for a month is from this equation. We can get the cost heat pump for a month is 32 per month. From this, we can calculate the difference between two costs. Is the month. That is from we can saving, the owner can saving for so this is a saving for the owner. Then we can get COP for HP, that is 5.2. So we get the COP HP heat pump, that is 5.2, and cost saving that is 134.67 per month. So that's all for lecture. From me of the lecture in second law of thermodynamic. Thank you very much.